because in Canvas, it will automatically start recording. Okay. All right, let's do this. Did we do this one last class? Can somebody look? Y equals x cubed, x between 0 to 4, and rotate about y-axis. Did we do that one? Oh, we did? Okay. All right, then. What happens if I give you the following? Y equals tangent inverse x. X equals 0 to 3. And bounded, oh, x equals 0 to 3, yeah.
You mean from 0 to 3? Okay, okay, got it.
X equals 0 to 3, yes.
Okay.
All right, set it up. So,
Rotate about the y-axis.
say again?
You want to rotate about the y-axis?
Y-axis, yes. Rotate.
Okay.
Actually, let's do x-axis first and then y-axis just to see what happens. We'll do both. So integral 0 to 3, 2 pi. Remember, this will give you tangent inverse x. Square root.
That's the
Average radius. Or actually, yeah, that would be average radius, and then you want the arc length. So 1 plus so we're going to have, actually, before you do this, I want to just rewrite this. This is xy. So 2 pi y square root 1 plus dy dx squared. I'm just writing the formula, and then you put the numbers in, 0 to 3. And the y will be the tangent inverse x. What is dy dx? Anyone?
It's the derivative of inverse of tangent.
Yeah, so that'll be 1 over 1 plus x squared. So put those in. So y will be tangent inverse x, 1 plus 1 over 1 plus x squared squared dx, 0 to 3 and 2 pi outside. And again, you can use Wolfram alpha to get the final answer. What happens if I rotate it about the y-axis? So this was part A. You're still going from 0 to 3. And actually, before I do 0 to 3. So look, I'm just going to draw a picture. It's still the arc length here, but you're going this way. The rectangle is going to be this way. It's this arc length is still going to be the dy dx squared. But what about the average radius? Did that change?
Yes, it changed.
Yes. What is the average rate? The average radius is the distance from here to here. Instead of y, what will you have?
I will have x.
You would have x. So this would be 2 pi 0 to 3x times square root 1 plus and you don't have to finish solving it, just setup is enough. Everybody okay with that? It's just the setup we're looking at. So 2 pi average radius arc length integrate, you got your answer for surface area. Everybody okay with that? So that vase project that you did, you found the volume of that vase. The next step would be to find surface area. Anybody who does that, find the surface area of the vase project that you did, you will get extra credit points towards the next exam. All right, now go to the handout from today. We're doing some physics applications, and we want to develop some calculus.
Do we need the handout?
Yes, you will need a handout. Please print it, because that way you won't have to write the notes and we can get to the examples faster.
All right, the printers still don't work here, so,
So pull it up on Canvas, and then the examples you will write by hand.
okay.
But you don't have to write the notes because they are here, and then when you go home, you can print them. Okay?
All right,
You don't really need them except for the problem, so that we can go through it a little faster. So first, just a show of hands, who has done like work done, moments, centroid, those physics concepts in calculus? Is there anybody who has not even heard of those? Put that in the chat. Okay, all right, we're going to do that. So we'll go a little slower. So have you taken any physics? No, no physics. Oh,
I'm
okay,
taking
all right.
physics
Then
right
we
now.
have to go slower, because if you have done it, sometimes the physics concepts are done a little differently than these. So I need to make sure, if you haven't seen it, then you're just going to follow what I'm doing. But if you have physics ways that are different than what I'm showing here, please learn these ways, because I want you to learn the mathematics behind it. But when you solve a problem, you can do it any which way you want. So let me ask people who have not done it, when you hear work done, what do you hear? Well, my homework. Homework is what? You do problems on your own. So there's time involved, right? And then your brain energy is involved. But if I gave you a book, so for example, if I used our calculus book, right? That's my calculus book. And in fact, let me get my document camera here. In physics, so if I have this, oh, this is too big. You can't really see that. Give me a moment. All right, let's see. This is my container of pens. So if I'm moving in a straight line and I apply force to it with no friction right now, so ideal conditions, there's no friction. If there's no friction and I apply force to it, the object is going to move. Can you see that? So in physics, the question is, what's the work done in moving that object? The work done in moving that object is force that's applied to it times distance. That is assuming you have ideal conditions and there's no friction, right? Does that make sense to you? But that is also assuming it's a constant force applied. So this is constant force applied. But what if it's a variable force applied? For example, imagine a huge tank of water. So imagine you have a huge tank of water. Let's say it's like a trough. I'll just make something up here. So you have a tank like this. And there's a spout on the top. We'll give it some dimensions. Let's say this is 8. I'll use the problem from I think it's one of your homework problems. Let's say this width is 3 meters. And let's see, this is height is 3 meters. And the spout is 2 meters up. Let's say it's a full tank of water. How much work will it be to pump water from here out to the spout? Will it be constant force for the work done, or will it be variable force? So if you look at the layer, because we are in calculus, of course, we're going to look at a layer of slab of water that you're going to lift up. Can you see that? This is the slab of water I'm going to lift up. At different heights, there is different amount of water because the volume of the water is going to be different, isn't it? Can you see that? The volume is going to be different. At the top, the volume is way more than the bottom, but the distance that each slab has to move is going to be all the way from here to here. That's the distance each slab has to move. And so the distance is varied also. Can you see? So when you have a variable force, of course, we're going to use calculus. So remember, we said work done is force times distance. Let's see, how can you use your calculus to figure that out? Well, this is like a rectangular slab. So the force that's applied to it, it's just its own weight, the gravity basically, right? Its weight is the only force applied. Now you just have to lift it out. So that's the distance, and the weight of the slab is the amount of force exerted on that object to move. And it's variable force because it's variable volume. Does that make sense to you, mathematically speaking? So let's put our axis somewhere here. Okay, we need XY coordinates. So I'm just going to bring that triangle like this. And we'll have the spout somewhere here. Why do I only have to worry about the triangle here? Because the rest is just times 8 for the volume. Would you agree? Okay, so I'm going to put the typical slab here. Let's put this coordinate XY. Okay, what can you tell me about this triangle and the relationship here? I have the width of this is X. The whole width would be 2X times this vertical height, which would be dy. Can you see why it's dy? Because it's vertical. I mean, you can use dx, but then you'll have to reverse the x and the y. So now the question is, okay, what about this coordinate? Is there a relationship between y and x? Well, if you look, this whole width is 3 meters, which means that from here to here, this width will be 1.5, half of 3, because we put our axis right in the middle. The height is 3. And this triangle, you can see like this. You have proportion triangle, the big triangle versus the small triangle. So in proportion means that there's a ratio. Or you can also think of this. So if you look at this as 3 and this as x, the whole thing as x, versus the coordinates here, you still will get the same eventual answer. In the textbook, they give you just a triangle, and in your web assigned homework, they'll just give you a triangle and not a coordinate axis. I like having coordinate axis because you can see what is happening. But if you do this, that's fine too. And then this is going to be 3 also. So look over here then. This is 0, 0. This is 1.5 and 3. So this equation is y equals mx. And our slope is rise over run. So that will be 2x. Everybody see that? Rise over run. So that is our relationship between the y and the x. So 2x dy will actually become y dy. Why? Because 2x is y. Everybody see that? Yes? Okay. You know that in calculus, we say what? If you have a function and you're taking bits and pieces, so you're going to take work done for all of these slabs, add it all up together and let the slab become teenier and teenier. Eventually it will become what? Integral. Can you remember? This is the process we've been doing the whole chapter 7. So our work is going to be integral. Integral for what? All the slabs. Where are the slabs going to move from? From bottom to top, all the slabs. So 0 to 3. Y coordinate is going to go 0 to 3. That's how the slabs are moving. Can you see that? Yes? All right, 0 to 3. Now, tell me, what is the force? Force is the volume of the slab. So let's get volume of the slab. What is it going to be? Volume of the slab is the length, which is the 8, times this width here, which is this width here, which is 2x. And the height is going to be dy. So the volume is 8y dy. And the force exerted on it would be volume of the slab times gravity. We're in the metric system, so this is meters, so that will be 9.8. So this would be 8y 9.8 dy. That is the force exerted on the slab. Tell me, what is the distance that it moves through? Each slab has to move how much distance? From here to here. All the way from here to here, it's going to be 2 plus 3, 5. All the way from here to here is y. How much distance is each slab moving then? All the way from here to the spout. How much? Anyone? How much distance is it moving from here to here? No one? Morgan said something, but her mic was muted. 5, okay? 5 minus y is the distance. So when you integrate force times distance, we're going to have 9.8 times 8 times y times 5 minus y dy. So 9.8 times 8, which is just a constant, you can pull that out. And then this will become, so tell me what that number is. Then 0 to 3, 5y minus y squared dy. What's 9.8 times 8? Somebody do it quick on the calculator. And tell me what you get. 78.4. All right. So this would be 78.4, 5y squared over 2, y cubed over 3, 0 to 3. And for now, you can just use Wolfram alpha or something. Give me the final answer. Everybody okay with the integration process, right? You're just plugging in numbers now, 3 and 0. And put the answer in there. Oh, that's 78.4. So that's the outside number. Give me the actual answer for the integration. Anyone? So this will become so work done will be 78.4 times 9 times 5, 45 halves minus 9. 45 minus 18. Okay, 1058.4 joules. Joules is the unit for work. For force, newtons. Work is Newton meter because we're measuring force in newtons and distance in meters. So Newton meter or joules is the unit for force in the metric system. In the non-metric system, you would say foot-pound. Pound is the measure for force, and foot is what you measure everything in distance. So look very carefully on this. Can you see how we can take a physics concept for constant force and change it to variable force? Everybody okay with that? Right? A similar thing can happen if you're working with springs. And so that brings me to Hooke's law. So I'm going to pull up my, so if you look, this is the force exerted, f of x dx. So if you look for Hooke's law says that if you imagine a spring and you put a weight on it, what will happen? It will pull the spring down, isn't it? It will stretch the spring. So Hooke's law says that in order to maintain, like say this is my normal length and I want to go from here to here, I want to stretch it this far. So that force that's required to maintain that stretch is proportional to x, the distance that I'm stretching. So f of x equals kx. That k is called spring constant, and that depends on what type of spring it is, what material that spring is made up of. That dictates what that k is. But this only works if x is not too large. Why? If you stretch a spring beyond what is allowed, what will happen? When you take the weight off, will the string bounce back again? No, it'll break, right? It will just remain stretched permanently, right? Do you know what I'm saying? So this formula only is valid for if x is not too large, because if x is too large, the spring will just break. Depending on the material that is made up of, some springs are more sturdier than others. Where have you seen springs in your daily life? Where are they? Give me some examples of where you use springs. Like you might not see them. Yes, cars. Where in cars are springs?
Suspension.
That's right. Right. And so it's very important to understand how springs work. So for example, let's do this first problem. A force of 40 newtons is required to hold a spring that has been stretched from its natural length 10 centimeters. So this is example number 1. So force applied is 40 and natural length of stretch from its natural length of 10 centimeters to 15 centimeters, which means that it's stretched for 5 centimeters. How much work is done from stretching from 15 to 18? So first of all, to do this example, we have to use Hooke's law. So Hooke's law states f of x equals kx. K is the spring. When you're working in the SI systems, you have to be metric system. That means meters. So this is all in centimeters. 5 centimeters is 0.05 meters. This is going to be 0.15 centimeters is 0.15 meters, 0.18 meters. So you are told that 40 Newton is the force applied in order for the stretch to go from 10 centimeters to 15 centimeters, which is 5 centimeter stretch. Can you see that? So 0.05, get me the K, 40 over 0.05. $800 or something? Yes. All right. So our f of x is 800x. Work done. You want to know what is the work done in stretching it from 0.15 to 0.18. And our function will be 800x dx. So 800 x squared over 2, 0.15 to 0.18, which will give you 800.18 squared over 2, minus 0.15 squared over 2, whatever that is. Can somebody look? And then that's how many joules. The units will be joules. Yes, William, that is good. Pens also have springs in them. Suspensions, yes, suspensions, pens, lots of places you'll see springs. You know those toys, like even little toys where like you press the spring and it jumps up, the frogs. Have you ever seen those? And printers have. That's correct, Nathan. Okay, did somebody come up with an answer for me? Tell me what you got. .96 newtons. Everybody okay with that? I know I'm out of time. We lost some time today. We will continue with this section next class period. So I would like you to try the second problem here. And looks like this third problem, 3A is what I just did. So try 3B. So you will do 2, 3B, and that's it. And then we'll start with hydrostatic pressure. And if you want me to repeat this work done, because this is first time you're seeing it, might be difficult for you. So I can redo this problem. So look over this problem that we just did and put it in this handout. Eventually, I'm going to have you load the handout, just the work done on the handout in the assignment in Canvas. So please make sure that you understand what this is like. I might give you a different kind of tank in exams, not these two, but in your homework also you have these tank problems. Okay? If you are able to read the rest of it, which is the hydrostatic pressure, how to find pressure on like walls of dams or tanks or just flat things submerged in the water, how do you do that? That's what we're going to do next. And then the next part that we're going to do is moments. Like if you were to take paper or even a pencil, basketball, whatever, you can balance it on your finger, right? How do you figure out where that point is? That's called the centroid. And so sometimes the centroid is not even in the shape, it's on the outside of the shape. But that's the next part. So we will do hydrostatic pressure and moments next class period. If you want to read ahead, you can, you don't have to. But in the minimum, I want you to do the circular spherical tank. How are you going to move water out of the spherical tank out? Okay? And then the spring problem, number 2. When you're doing it, now this is measured in pounds, so work done will be foot-pound. The unit will be foot-pound. Okay, that's it for today. If anybody has questions, I'm happy to stay. Otherwise, we'll continue this section next class period. So homework 7.5, I forgot when it's due. Somebody look it up. Might be due tomorrow.
I think it's due today.
Today?
Yeah.
Okay, I'll make it. Is it okay for it to be due today? Is everybody okay with that? Anybody who wants me to move it to tomorrow? Okay, so let me know if you struggle with it. I will help you today if you're stuck in it. But it's really just what? 2 pi, average radius, arc length. Doesn't matter what you revolve around. Everybody okay with that? For surface area? So when you do your homework, it's just surface area problems, that's it. Okay, we will start 7.6, we'll continue 7.6 next class period. Sorry about the beginning of class, we lost some time because Canvas wasn't working. The Zoom wasn't working.
Yeah, we had a huge accident on the freeway today coming up here.
Really?
Oh yeah, that's why I
Oh,
was
no.
late. And
What
then
happened?
it was raining and pouring at the same time, and then they were like the freeway was all backed up like maybe 10 to 15 miles. So
Oh my goodness.
yeah.
That's too bad. Hope whoever was not too hurt.
Yeah, I hope so.
Yeah. Well, you all stay safe. Have a wonderful rest of your day. Bye.
So for Hooke's law, what are the labels? Like, so
For the Hooke's law, what was the question?
what are the labels like? So is it just Newton's?
Oh, you mean the
Or-
units?
Yeah, that's what I meant. Sorry.
Yeah. So for Hooke's law, measures the force. So that's Newton's, yes.
Okay, and then
And when you do work, it will be joules.
okay, so the 0.05 is just a distance.
Right. So the natural length of the spring was 10 centimeters, right? And then you stretch the spring 15 centimeters, which means that 10 to 15, that's a difference of 5 centimeters, which means whatever its natural length was, you stretch the spring 5 centimeters.
So the label for K would be Newton meters, or Newtons per meter.
Yeah, Newtons per meter. That's correct. Because the X is measured in meters. That's very good. It's like slope. You know, it's like a rate of change. K is the force required per meter of movement in the spring. That's how you
Okay.
can think of K as, like Newtons per meter. How much force per meter is required? That's what the K. And that's specific to that particular spring, like whatever material it's made up of.
Okay, so just like a constant for each.
It's a constant. So whatever material, like if it's made up of steel or iron or whatever, it will have a specific, whatever the material density, there's lots of factors that go into figuring out what that constant is.
Okay,
Yeah, that constant is
But
the,
these are known constants for the particular materials.
okay.
Yeah.
Is this what, like, do you do a lot of this? Is this just like physics? Like,
Physics, yep. This physics engineering. So this is how, when you go to a physics or engineering class, or it will say it's calculus-based physics, then you will be seeing this kind of applications there. Right, until now, we were just doing normal problems, but now you're seeing how it's applied in physics or engineering for that matter.
all right.
In fact, I think Fresno, you took physics with Joe Otu, right?
yeah, I'm taking it right now. Yeah.
You're taking it right
I
now.
did.
Did you see anything
Yeah.
like that yet?
Yeah, it's not similar, but it's the same concept. Like
Right, but
the
it's done just a teeny little different,
yes.
but it's
Yeah.
same concept.
Yeah.
And you will use integrals also, right?
Yeah.
Yeah.
Yeah, I wanted to take physics, but they didn't they had a lab at like at night, so I couldn't do it.
Okay.
And I don't think Washington County offers physics 1 next semester.
Oh,
I have
yeah,
to
they
look.
also, it's only offered in fall, I think.
Yeah,
Yeah,
I
yeah,
wanted to take it though.
yeah, yeah. But this is the kind of stuff you will see in it. I mean, we're only doing like a small sliver of it. You're just giving you a glimpse of what is done. You will do it
Yeah.
in much more detail in physics classes.
It's super cool.
Yeah.
So,
All right.
all
What
right,
else?
I'm good. Thank
Okay.
you.
All right. Bye.
Bye-bye.
Bye. Fresno, any questions? How's your dad?
Doing better. Thank you.
Okay, good.
Doing much better. I talked to him this morning.
Oh, good. That's
Yeah.
good.
Yeah,
That's
he's
good,
he's
that's
probably gonna leave the hospital by tomorrow.
Oh, wow. That's such a relief.
Yeah, it is.
I
It is
can
a
see it in
structure.
your face.
Yeah,
You're a
I
little
feel
more
much better.
relaxed.
Yeah, I'm a little more relaxed.
Oh my God.
So
That's
yeah.
good. That's really good. That's happy news.
yes, it is.
It's gonna
Yeah.
be a great day today.
Yeah, it is. It is a great
Yeah.
day.
All right.
One more thing.
Yeah.
I have looking at, I was looking at my exam, my take-home exam.
Yes.
So do you want me to correct what I
Yep.
did and then send it to you
Nope.
of what I
You
did
won't Send
wrong?
it to me, but when you're ready, you will meet with me and then I will
Okay.
ask you oral questions.
Yeah, part of me, I don't want to because I really want, you know what I mean? It's like,
Why don't you want to? You want to give
No.
up, don't you?
no, I don't want to. It's just that I don't know. It's just the way
It's
I've been.
depressed. You're depressed.
Yeah, kind of.
Because
but
I think this is the first time where I think until now I have never seen you struggle, and this is the first time when you have hit hit a teeny little hiccup. But if you are a tutor, and what do you tell your students to do?
Yeah, that's true. That's true. I
What do
will
you
say
tell
don't
them to
give up.
do?
Don't give up.
Aha.
Don't give up.
You don't
Yeah.
just say don't give up. Don't you tell them to go talk to the teacher and see what went
Yeah.
wrong?
Yeah, exactly. No. I'm willing to give it a shot. It's just
Okay.
that I'm willing to give it a shot. It's just
Okay.
even of the circumstances, I feel like I put pressure on myself that I could have done better than that, even
Of
in the
course you could have done
circumstances.
better. If the
You know what I mean?
circumstances, if you did not have all that stress, of course you would do different. Let me stop recording. Give me a moment.